Hello and welcome. In this video we are going to introduce ordinary differential equations and talk a little bit about why we would use them and how we model real-world phenomenon with them. So an ordinary differential equation, or an ODE, is an equation that contains at least one derivative in it and that has exactly one independent variable. So you may have, if you've taken a multivariable calculus class and you've seen more than one independent variable, that is specifically y. That is a multivariable class where you focus on there being more than one independent variable. And the word ordinary and the fact that there's only one independent variable go hand in hand. There's another class that would follow this one called partial differential equations, or PDEs, and PDEs would be equivalent to the multivariable calculus realm in that here you would say have one output but multiple input variables. So in terms of how this works as a function, so an ordinary differential equation is an equation, and it's typically a function, but the way this works is that you input, in this case, well, you might be saying you're showing two variables here, but we have one independent variable, which is typically referred to as t or time in a lot of instances, and then your dependent variable is y. So in this odd, strange world that we're entering, the inputs into dy dt, this function, the rate of change, can potentially depend on up to two variables, the independent variable and or the dependent variable. So you plug these values into your equation, and what do you get? You get an output of dy dt, which is a rate of change. Another way you've probably seen this written before is as y prime, and that's equally acceptable. The dy dt notation is nice because it emphasizes that this is the change in y per a very, 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 very small change in t. So the fact that we're outputting a rate of change is a little bit different. Now in a Calculus 2 class, in an integral calculus class, you've encountered solving these already. You would integrate to try to obtain the original function y. And that's the purpose of differential equations, is the goal of modeling a scenario with an equation that outputs the rate of change dy dt is to ultimately get information that allows us to determine y for any given t. We do this because modeling rates is often significantly easier than trying to model amounts. So it's often easier to model how fast something is changing and then use calculus to determine what distance that, or if you're talking about speed, it's easier to model speed and then to solve that speed equation for distance versus time, and calculus allows us those tools. So here are a few examples of differential equations. So in this case, you see that the second derivative of y with respect to t is negative 32. That's a differential equation because it involves one or more derivatives. Could be first derivative, could be second derivative, could even be a mixture of first and second and third and so on, higher order derivatives. Dy dt equals t squared. These are nothing new. These are equations that you would have seen in a integral calculus class. Dy dt equals 3y minus 2t. Well, that's a little bit new. In this case, we see that the rate of change, the output of this function, the dy dt, depends on or accepts two input variables, one independent variable and one dependent variable. Specifically, you need to know the value of t and the current value of y in order to compute how fast that quantity is changing. So that's a perfect example of what we have going on here. Here we give the function a value of t and y, say 1 and 1, and in that case we'd have 3 times 1 minus 2 times 1 is 1, and that means that y is changing at a speed of 1 unit per unit time. Here is just a mixture of, you have a second derivative plus a function of a first derivative plus a function of y equals a function of t. This is called a second order ODE, and the order comes from the highest derivative present. So this would be a first order This would be a first order, and this would be a second order. So you always look at the highest derivative present in that equation to determine its order. More on that a little bit later. So the types of differential equations that we might encounter is the one that you've already learned how to solve with different integration techniques, which is what I like to call the solution method, the Calc 2 integration method, the stuff you learned in Calculus 2. Those equations were of the form, you had like y prime and then you had some function of t. Probably instead of using t, you may have used x, so dy dx is a function of x. And that was no problem. You could just integrate the equation using certain techniques and determine y versus t. In this case, notice the dependency. The dependency is what does the rate of change depend on? Well, it only depends on the value of t. Here, this method that we'll learn later, separation of variables, applies to situations where the rate at which something is changing is a function of the dependent variable. So the rate depends only on the value of y. This is called an autonomous ODE. Like if you think about automatic, something that is capable of running itself, autonomous cars that drive themselves. So in this case, you see that the rate of the dependent variable depends on the value of the dependent variable. Well, where would you see that? We'll look at a couple of examples shortly, but one context is where the rate at which a population is changing is usually not dependent on what year it is, but how fast a population is growing probably depends on how big the population is, right? Because if you think about only 100 couples, for example, can only produce so many kids, but 1 million couples could produce way more kids. And so typically when we model populations, the rate at which the populations are growing or decaying is a function of the population size itself. And we'll look at some situations naturally that you'll find, well, how the heck would an equation involve both t and y? And we'll encounter those later on. So when we solve differential equations, our thought process often follows these steps. Clearly define your variables, right? So we want to know, okay, what's time? Is time measured in hours? If it is, hours since when? Y, what does y measure? Are we looking at population size? Is it population size of elk in millions of elk? We have to be very clear in defining those, because defining those will tell us the units of dy dt. We write the model assumption. What do we want to assume about our population? Does it tend to grow fast in July but slow in August? Or is the reproduction rate constant? You make some assumptions. Then you use those assumptions to write your differential equation. Then you typically solve it if you can, and you obtain an equation for y versus t. You analyze it, answer questions about it, and if you feel like those assumptions simply weren't good enough, or you want to refine the model, you refine it and repeat steps 3 through 5. So let's take a look at one equation that's already written for us. Consider the skydiver model, where y is a measure of the skydiver's height from the ground, t seconds after jumping from the plane. So dy dt equals negative 32t. Suppose a skydiver jumps from the plane at a height of 15,000 feet. Solve and determine how long it takes for the skydiver to drop a total of 1,000 feet. So to do this, let's first take a look at our units of dy dt. So dy dt is no different than what you may have written in an algebra class as delta y delta t. But the difference between these notations is that this could be over a longer period of time. You may want to know how fast the skydiver was falling on average across the entire drop. But this equation tells us instantaneously how fast that skydiver is falling. So dy dt, in all of its glory, has the same units as delta y delta t. And its units are going to be, well, y, the change in y is going to be measured in skydiver's height from the ground. We should have probably said this is going to be in feet. So this is going to be in feet, or change in feet, divided by change in seconds. So really, this equation models the speed of the skydiver at any given moment. So let's do a little bit of analysis on this, because we see that dy dt depends on t only. So at time 0, this is basically the skydiver, and here's my fantastic rendition of a plane. We'll have it going this way. There's the wing. Kind of looks like a finger, but Hey, good enough, right? So here's the port where the skydiver is going to jump from, and at time 0, the skydiver hasn't jumped from the plane yet. So at time 0, if I plug in 0 for t, negative 32 times 0 is 0. And again, this is feet per second. So before the skydiver jumps from the plane, their altitude isn't changing yet. 1 second later, 1 second after the jump, physics tells us the skydiver should be falling at a rate of 32 feet per second. Now the reason it's negative is because this is the height from the ground, right? So the distance as time passes is going to get shorter and shorter and shorter, etc., as opposed to the distance from the plane, which gradually gets larger and larger. But we are decreasing our height from the ground. So that's the key here. After 2 seconds, wow, the skydiver is falling at a very rapid speed, right? Because this is what we often attribute to the effects of gravity. So, acceleration due to gravity. So there's some acceleration built in here. The way we would solve this equation is we want to basically integrate dy dt, and we know that if dy dt is negative 32t, then what would the function that we started with, I'll call this y of t, that like f of x, but y of t, what function would you have to take the derivative of to end up with negative 32t? Well, I know it's going to have to be a quadratic, because what I'm really asking calculus-wise is what is the integral of negative 32t? And let's see, I'm going to add 1 to the power and divide by that new power. That's going to give me my function, but wait a minute, when I took the derivative of this quadratic function, there could have been an arbitrary constant attached to it. Right? We have to say, when I take the derivative of my y function, do I end up with negative 32t? So this one gives me negative 16t squared plus c. And if I take the derivative of negative 16t squared, I do indeed get negative 32t. If I take the derivative of a constant, then I do get 0. And so we have to have that constant there because this constant is going to help us satisfy our starting condition, our initial condition. So we have that our function, y of t, is negative 16t squared plus c. Now this is an equivalent but alternative way to think about this. Alternative thinking, this is more of an algebraic way of thinking about solving a differential equation. So if I have an equation, and I'm going to get the same answer. This is nothing different. It's just a slightly different way of thinking about it that leads to the same solution. And you're going to find that sometimes shifting your way of thinking can be very helpful. So as long as I do the same thing to both sides of an equation, i.e. integrate with respect to t on the left and the right, then I'm maintaining balance in the equation. So what I'm doing here is just algebra. And on the left, I'm integrating dy dt with respect to t. On the right, I'm integrating negative 32t with respect to t. So I've written this in black just so you can see that I haven't changed the two sides. I've just performed an operation on them. Now, what do you do? What do you get when you integrate the derivative of y? Well, if you take the derivative of y and then you integrate it, you get the original function back. And that's one beautiful thing that we know about calculus. If you start with f of x and you take the derivative of that with respect to x, you get f prime of x, or df dx. But then if you integrate it, if you integrate with respect to x, you get your original function back. And this is often a piece of the fundamental theorem of calculus. So if you integrate a derivative, you get your original function back, y. And now if you integrate negative 32t, you get negative 16t squared plus that constant. So notice they lead to the same solution, same result, different ways of thinking. This one's more a little bit more conceptual. This one's a little bit more algebraic. Okay, so now that we've solved it, we have to come back up here and say, well, how am I going to obtain information about the starting value of c? Because I need to answer how long does it take for the skydiver to drop 1,000 feet. So not to get down to 1,000 feet, but we want to know how long will this feet to get, we're starting at 15,000, So we want to ask, when is this skydiver going to get to 14,000 feet? And we want to know what's the value of t. So these little diagrams can be very helpful to help you figure out what is it that you're looking for, and then you can develop the tools necessary to get there. So my initial condition, we're going to refer to this as the initial condition, or sometimes you'll see it abbreviated as the IC. Okay, and the way I could write this initial condition is in a couple of different ways. I could say that t naught, y naught, that this 0 indicates initial, is the ordered pair 0, 15,000. So it just means that when t is 0, y needs to be 15,000. Another way I could write this is y of 0 equals 15,000, and that's just function notation. So you could write it as an ordered pair, or you could express it as a function. All right, so we're almost there. Let's go ahead and find that value of c. So to find c, we have to solve for our initial condition. Or we have to solve for c by using our initial condition. Y of 0 equals 15,000. So what does that mean? Well, that means I'm going to replace y with 15,000. I'm going to replace t with 0, and I'm going to solve for c. So, of course, this term is 0, and I end up with c equals 15,000. All right, so my final answer is going to be y, or y of t, either way is fine, is negative 16t squared plus 15,000. Okay, now in this, our approach to solving things like when, for what value of t will y be 15,000, we can solve this with a graphing calculator, something like desmos.com. So let's go ahead and see how we would solve when, for what t, we now need to find for what t is y equal to 14,000. We want to know how long does it take for that skydiver to drop. So I'm going to go ahead and hop over to Desmos and show you how to do this. All right, so here we are in desmos.com. This is what it looks like, and it's very easy to use. You just click on Start Graphing. There are lots of different features here. You can actually log in. You can share your graph. You can see I'm already logged in here. You can title your graph, so if you want to save it, come back to it later, have it for reference, perfect. There are a few things you can do in here. You can't actually put an image on the graph. Well, I don't think we'll have a need to do that, but you can actually enter a function, you can give yourself some notes, put in a table, put in a folder. Especially if you're going to have a lot of things, having a folder is convenient, because what you can do in this folder is you can say add an expression. So what I'm going to plot is, I'm going to call my function f of x. You could just say y equals, but I'm going to use f of x. That way I can show you how to insert a table as well. Negative 16x squared plus 15,000. You're wondering, why am I not using t? Well, if I try to use t, you're going to see that we're going to get a little caution thing over here. And also, nothing really shows up. Oh, I guess it does. Interesting. So probably should stick with x. It's going to ask us to add a slider, so it's x and y are your safe variables. And you can see there's the function. When x is 0, the skydiver is at 15,000 feet. And clearly over here, the skydiver is not going to be falling for more than 30 seconds. And that's free fall. So lots of things that are actually going on in this model here. But over here on the little wrench, you can change things, like you can change the type of grid if you don't want the grid on there, remove minor grid lines, major grid lines, etc. You can have arrows on the axes. You can play around with those things. I'm not really sure what these are to be. Oh, look at that. You can change the way your equation shows up. I know nothing about that, so I will not comment on that at all. So x-axis, well, this is going to be my time. So in here I'm going to put time, t. You can see that that shows up down here. Along my y-axis, I'm going to call this the sky height from the ground in feet. And I'll call that variable y. And time down here, I should have said time since jump seconds. So now I can change my x-axis range and go from, say, 0 to, probably don't want to go higher than 32 seconds or 30 seconds because that's about the time the skydiver would theoretically hit the ground, although hopefully their parachute would come out. And now we'll go to about, I'm going to go to 15,500. That way I just get the full picture. And now I can zoom out a little bit if I want to, or I can zoom out in and out here as well. If you press the home button, that's going to change you back to your default zoom, the default settings for the graph, so be careful with that if you spend a lot of time doing this. So I want to know, and by the way, by creating this folder, notice that when I put that arrow away, that just makes sure it's all part of one folder, so I could call this skydiver function. Oops. And so that way I know that that's what that folder will contain. You don't have to create folders, it's just convenient. And now I'm going to graph another one. I'm not going to put this one in a folder just because we're not going to be doing a lot of stuff on here. But I want to graph y equals 14,000. And what that means is that these are all the y values where the height of the skydiver is 14,000, anywhere it intersects our blue curve. You don't want to just insert 14,000 because it doesn't really know what that means. You have to say y equals. And the cool thing about this is you see all these little snap points. So if I click and drag with my cursor, you can actually snap to these important points here. Intersections, zeros, vertical, horizontal intercepts, etc. So we see here that it's going to take about 7.9 seconds to reach the height that we are seeking of 14,000 feet. So the skydiver will basically be in the air for about 7.9 seconds. T is about 7.9 seconds. And so just to kind of reproduce that graph that we had here, it looked kind of like this. And this value here was 7.9 comma 14,000. So after you've solved your differential equation, feel free to use Wolfram Alpha, or Desmos in this case, to help you answer those questions about your final function. You could solve this by using quadratic formula or doing some algebra, but honestly, we have bigger fish to fry. So we've solved our first differential equation here. This was something that we didn't really need to know anything new about, but hopefully our thinking has adapted a little bit to seeing how the input of our function, or the output of our function, is a speed, a rate of change. I'm always going to say speed, even if it's people per year. I mean, that is a speed, right? It's a type of speed, the speed at which people are growing into the population or leaving the population. In this next problem, let's actually go ahead and build the differential equation model for it. Now I know it's going to be really, really tempting for you to actually solve the equation without writing the rate of change, but eventually that will become impossible or very, very, very difficult. So we want to start thinking in terms of rate of change. Suppose that at any given time, water flows from a faucet into a bathtub at a rate of 8 gallons per minute. Assuming the tub is initially empty, how much water is in the tub after 13 minutes? So let's start off with our modeling process. We first define our variables. So it seems like what we want to keep track of, our y variable, you don't have to call it y, but we want to keep track of the amount of water in the tub. So water in tub, measured in gallons, and T will be time in seconds since we begin filling up. Since filling up begins. Okay, let's think for a second about what the meaning of dy dt would be. So because y is measured in gallons, we would have change in gallons divided by change in seconds. So the units of dy dt are going to be gallons per second. But that's exactly what we're given here. We're told that the tub, the rate of change of the amount of water in the tub, it's gaining 8 gallons per minute. So this equation, believe it or not, is simply dy dt equals 8. dy dt, again, keeps track of at what rate is the amount of water in the tub changing at any given second? Well, it's always filling up at the same speed of 8 gallons per minute. So there's no variable to go along with this. It's simply constant rate of change. And if you were to plot this constant rate of change function, if you were to graph dy dt for any given time, it would be a flat line at 8 gallons per minute. It's always filling up at the same rate. So what we want to know is we want to ultimately know what's the total volume, right? So if you multiply gallons per minute, times minutes, you're going to get total gallons. And so we're going to do a lot of dimensional analyses here. And anytime we're talking about finding areas, that's the purpose of what integrals do. They accumulate area for us, at least geometrically. So to solve this, I'm going to take the algebraic step here. I can also ask, okay, if I want to know the amount of water in the tub, and you may already have jumped to this. You're like, well, I don't need to solve this differential equation. I already know it's going to be 8t plus 13 or something like that, or 8t plus 0. But to solve this, let me go ahead and integrate both sides. So what I'm asking is, what function did I have to take the derivative of to end up with 8? Well, that same question can be answered by saying, what is the integral of 8 with respect to t? And that's going to be 8t plus c, and the integral of a derivative is the original function, and so we get y equals 8t plus c. Our initial condition is the ordered pair y at time 0 is equal to 0, right? So how do we know that there's initially at time 0, there are initially 0 gallons? Because assuming the tub is initially empty. The tub is initially empty tells us what that initial condition is. So to find out what c is, I've got to plug in 0 for y, 0 for t. And we do want to go through this process because eventually c will not always end up being whatever your y naught is. In this case, we do get c equals 0, and we end up with a final function y equals 8t. All right, now we can answer this question. How much water is in the tub after 13 minutes? That's going to be answering the question, what is y of 13? And we could also write this as y of t. I'll do that. Y of 13 is going to be 8 times 13, which is 26, 52, 104, I believe, 104 gallons. And you probably could have just figured that out without doing any calculus. If the tub's filling up at 8 gallons every minute, and you do that for 13 minutes, then it's going to have 13 copies of 8 gallons in there. And I use the word copies to emphasize that we're basically reproducing 8 gallons every minute. Perfect. Well, this leads us to what I call the ubiquitous bathtub analogy. The bathtub you can think about as the amount, right? The amount of something. So it doesn't have to be limited to water filling up a tub. But in this case, you can think about the water level as population level. How big is the population size? The inflow, which you can think about as the water coming into the tub, could be things like births, immigration. You might have multiple sources that feed water into your tub that make your population level rise. On the outflow, or the drain, these are any things that will affect your population in a negative way. So culling, starvation, weather, disease, old age, accidents. Culling is like, could be, if you're talking about fish, it could be fishing. If you're talking about elk, it could be hunting. Culling is the process of removing creatures from the population. Okay. Take a look at a couple more examples here of modeling. Let's say that we let y represent the number of elk in a particular region of Flagstaff t years after study begins. So our variables are defined for us. Suppose it is known that 13% of elk successfully give birth each year. Complete the following differential equation modeling this scenario. So dy dt is going to be measured, first of all, in elk per year. How do we know that? Well, y is measured in the number of elk. T is measured in years, therefore our rate of change model will be elk per year. So the question we have to ask ourselves is, how many new elk do we expect to have each year? Well, it's going to be 13% of the elk currently there are going to give birth, right? So if, for example, there were 100 elk, then we would expect 13 new elk over the course of that 1 year. That is, at that moment, we would expect the population to be growing by 13 elk per year. Now we know that not all births are successful. We know that there are all these other things that are coming into play, but we're not going to take those into account right now because we're building a model simply based upon this one assumption that the population is growing by 13% per year. We don't need to become the scientists. The scientists are the scientists. They tell us what the model assumptions are, and we build those in. Okay, so if there were 200 elk, well, 13% of the 200 are going to give birth, so that means there are going to be 26 new elk in that, or the population will be increasing at that rate. At 300 elk, same kind of process. 13% of the 300 are expected to give birth. That's 39 elk per year. And you're probably seeing the pattern. Here, we're just taking 13% of the 100. Here, we're taking 13% of the 200. Here, we're taking 13% of the 300. And in general, I like to do this in general thing. If there were Y elk, because Y is the variable that tells us how many elk there are, then I would have 13.13 Y elk per year as an instantaneous rate of change. So it's always 13% of whatever our population size is. And that is the reason why our differential equation is now, for the first time ever, well, maybe you've seen these types of equations in your career in your education, but this is a differential equation that is a function of the dependent variable, also known as an autonomous ODE. Pretty cool. We don't know how to solve this because it involves the dependent variable in it. And we'll soon learn a technique that's actually pretty simple in concept that's called separation of variables that will help us solve this equation. But we'll come back to that later. That's not the purpose of this video. Let's look at a more complex modeling situation. How do we realistically model? How do they know that it's 13%? So suppose a population of elk in Flagstaff is to be modeled over time in years. We would like to know the number of elk in the population at any given time. The following information is available. And I think I took this from Wikipedia for the gestation period of female elk. Female elk have a short estrus cycle of only a day or two, and matings usually involve a dozen or more attempts. Okay, we're not going to take that into account because how do I deal with that? By the autumn of their second year, females can produce 1 and very rarely 2 offspring, although reproduction is most common when cows, that's I think the name for the female elk, weigh at least 200 kilograms. The gestation period is 240 to 262 days, and the offspring weigh between 15 and 16 kilograms. So there's lots of information here, but ultimately all I want to know is, okay, well, how many new elk are going to be born? So what is dy dt going to be? Same units as before, elk per year. So what's going to affect them? Well, obviously the weight will, right? The mass of them. Are they of the proper mass? This estrus cycle of only a day or two, I mean, that's negligible. That's really small in terms of years. So 1/365th is probably not going to have a huge impact. So I'm going to go ahead and ignore that for now. Dozen or more attempts at mating. I don't know how many times they mate. This doesn't give me enough information to go off. All I do know is that if I did have Y elk, if I had Y elk, well, first of all, Y elk doesn't allow me to determine how many new offspring are going to be born because some of those are male, some of those are female. So I'm going to make an assumption, assume 50-50 female-male split. Okay, so that means of the Y elk, 50% of them are female. These are female elk. And we're going to make the assumption that every female elk is going to successfully give birth, because I don't know how else to do it without taking into account other information that I'm not given here. Now, I have to figure out, it's not the case that if I had 100 elk, that there would be 50 new births, right? That every single female would give birth to one calf per year, because it actually takes less time. It takes less time than a full year. So this is the female elk, but keep in mind that my units need to be in elk per year. So this actually tells me the number of elk, but not with respect to time. So in order to get elk per year, I have to divide this by how long it takes to produce those elk. Well, it takes 240 to 262 days, so I'm going to make another assumption here. And again, I wouldn't expect you to be able to do this right off the bat, but as just a modeler, how do you approach these problems? We're going to assume, or I'm going to assume, that halfway between this, that it will take 251 days to give birth. Now, I'm not an ecologist. I don't know how this works exactly, but I'm going to make this assumption that every 251 days a new calf will be born from every single female. And again, not a good assumption, but it's the best that I have to go off of. Now, I can't use days, I need years, so 251 days is 251 365ths of a year, assuming there are 365 days a year. So if I divide this by 251 365ths, that's in years. This here is in elk, and I now have elk per year, which if we do the division of 0.5 divided by 251 365ths, we get about 0.34 from that. So this component here is going to tell me that I get 0.34y. Now you can see that that's less than 50%, because 50% of the population is female, but and my mistake, this is not 0.34, this is actually 0.73. Because I multiplied 0.5 by 251 over 365. And so this makes sense because if you think about it, even though 50% of the population is female, it doesn't take a full year for each female elk to give birth, and we assume that every 251 days, every female on average is producing one elk. And so that means that over the course of a year, we expect that to be a little bit bigger than that 0.5. So my model for this equation, after all is said and done, would be 0.73y. So with other types of models, where we're not modeling population, we take a very similar approach. This last example is a non-population model, because of course we're not always modeling populations, but it's a famous one. It's called Newton's law of cooling. And Isaac Newton, among others, observed that the rate at which something cools or heats up is negatively proportional to the difference between the temperature of the object that is getting cooled or heated, T, and the ambient temperature, T naught. So let me draw you a little picture of what we've got going on here. We have some sort of object, let's say a cup of coffee. So here's our cup of coffee, and there is our little handle. And so we have this hot coffee, right? And we put it inside of a room, right? We put it inside of this room, and inside of this room you have your thermostat. And of course, there's going to be some temperature of this room. Maybe that room is 78 degrees Fahrenheit. So not a bad temperature for a room during the summer. And this coffee cup, or the coffee inside that cup, has a temperature that of course changes with respect to time, right? So little t is time, capital T is the temperature, and the temperature of that cup of coffee just depends on the time, right? So this guy is going to be cooling off, especially if it's piping hot at 160 degrees Fahrenheit. So we might actually say that the temperature at time 0 is 165 degrees Fahrenheit, for instance. But what we really want is we want to model the rate at which the temperature changes per unit of time. So let's read this and translate this carefully. It says the rate at which something cools or heats up is negatively proportional. Okay, so when we see negatively proportional, what that means is that, first of all, it's negatively proportional. Well, there's going to be some proportionality constant, and proportional to means it is multiplied by that constant. And so it's negatively proportional to something, right? Negatively proportional to the difference between the temperature of the object and the ambient temperature T naught. So the difference between them is T minus T naught. And it has to be done in that order because look what happens. So K itself, K is the proportionality constant, and these constants are always going to be greater or equal to, I shouldn't say equal to 0, that wouldn't make much sense, but is always greater than 0, right? So the constant itself could be like an R rating for insulation of a house that tells you basically how much insulation capability does that, insulative capabilities does that insulation have. And the reason it needs to be T minus T naught and not T naught minus T is, let's think about this for a second. So if I have 165 degree coffee minus a 78 degree temperature, this is going to be a positive number right here. Now, what I have here is this is going to be a negative number, right? Because it's going to be the negative of a positive constant. And when I multiply those together, I am going to have a negative times a positive, which is negative. So that tells me that the rate at which the coffee mug is changing is the temperature change is negative, which means the cup is cooling off. If, however, you switch these around and you wrote T naught minus T, now let's think about this. So the temperature of the room is 78. Temperature of the cup of coffee is 165. That quantity right there is negative, right? This is going to be negative. This quantity right here is going to be negative, and when you multiply a negative by a negative, you get a positive, and this suggests that the coffee is heating up. And I'm going to put a big question mark and exclamation there because clearly this situation doesn't make sense. How could a hot cup of coffee start heating up in a room that is cooler than the cup of coffee? So sometimes these little details make a big difference in our modeling approach. We'll go ahead and stop there with this video, and we'll get more into how we begin solving equations like this. In fact, this one here is also autonomous, just like the rate of change model above.